So how'd you do? Did you get the right answer? The combined torque of the boom and the load is 414. Safety factor 1.5. That's what you get. So that's the amount of torque you need to keep the crane from tipping over with the safety factor. So you need 621 inch-pounds. You've only got 140. What's the difference? 481. That's the added torque you need, not the counterweight. That was my mistake. You need that much torque on the crane side. That's why I had to put in all these counterweights. But this is counterweight, not torque. So how do we get the counterweight? We need 481 inch-pounds. Divide by 24 inches, and you get 20 pounds. Simple. So that's why I ran out of bricks, so I had to use the steel to get about 21 pounds. Okay, now we've got a totally different situation. Not a crane anymore. Now it's a lift bridge. Remember a couple videos back I said this was going to be a lift bridge too? Like in the old movies when they had a drawbridge across the moat, and a couple of guys up in the tower were using a windlass to lift it. Well, I'm going to tell you the math about the windlass later, but for now we got something more important. So, again it's torque, but instead of the pivot point being here, forget about the crane. We're not going to use the crane at all. So instead of the pivot point being here, it's here. Where the deck, this is not the boom anymore, it's the deck of the bridge. That's where the deck pivots, right? But we still have torque. The weight of the deck is pulling down gravity. What's holding it up is this string. I'm not going to call it line, I'm going to call it string. You'll see why in a minute. So it's the same thing. There's got to be equal torques on both sides. The torque of the pulling down on the deck and the torque pulling up. And that is a little different. So here's the deck, 36 inches long. Remember, it's the same length as the boom. And here's the string that's holding it up. So the torque of the deck is the weight, which is 5.5 pounds. I got a better measurement. And the distance is 20 inches. Remember, when you measure from the CG of the deck 20 inches away from the pivot. That red dot is the pivot now. So the torque we have is 110 inch-pounds. Now, think of it as that's a clockwise torque, meaning when this rotates, it rotates in a clockwise direction. And what's opposing it is the counterclockwise direction. So the string pulling up makes a counterclockwise motion. But if everything is balanced, which it is now, as you can see, then the torque on this side pulling down, the weight of the deck pulling down, has to be equal to the torque pulling up, which is the string. Here's we got a 30-degree angle on the string. Okay. 30 degrees there, and we've got to figure out the torque of the string pulling up. So it's not the weight of the crane or the weight of something else, it's force. It's the line of force. Imagine these two guys up here are pulling. It's their force that generates the torque. And if torque is force times distance, remember it's not force, it's weight. Because there's no weight here, it's the force of the guys pulling. So the force times distance has to give us the same 110 because it's balanced. If it was moving, the two numbers would not be equal. Just like when you have the seesaw. When it was balanced, the torque on one side equals the torque on the other side. Counterclockwise torque equals clockwise torque. So torque is force times distance. So first we have to figure out what the distance is. Now remember, here's the line of force, which is actually the string. And we measure from the line of force directly to the pivot point. So here's that imaginary line, which is not imaginary because you can see it. There it is. And the shortest distance is at right angles to the pivot point. Just like over here, everything we were doing was the shortest distance from the line of force to the pivot point. Gave us a right angle there. We've got a right angle there. If the string is a 30 degree angle, we've got a triangle here. There's a right angle. What's left? 60 degrees. Remember cosine from the last video? Adjacent over hypotenuse? Well, there's the adjacent, there's the hypotenuse. The hypotenuse is 36 inches, just like before. Now we've got to figure out what the distance is. So if cosine is adjacent over hypotenuse, and the cosine of 60 is 0.5, if you remember from last video. So if we substitute everything in and switch things around, instead of adjacent, we've got the distance. That's what we're trying to find. Instead of the hypotenuse, we've got 36 inches. So with a little algebra, the distance is 18 inches. Now that's 18 inches is the distance. What's the force? Hold on a minute. The total torque is 110 inch-pounds, because that's the torque pulling down. The clockwise torque has to equal the counterclockwise torque. So we know the torque, we know the distance. All we need is instead of weight, force. Do a little algebra, and the force is 6.1 pounds. So that means if there was no windlass and we were just trying to pull up here, we need 6.1 pounds of force or muscle to keep the deck level. Now the next video I'm going to show you will be different, because what if we put the string instead of a 30 degree angle, a 60 degree angle? Would that be more or less force, muscle that we'd need? That's tomorrow. Can I turn on the damn thing?